Um, Hello, I'm Yasir. Today I will try to apply the second order Runge-Kutta method to the SIR model. So for doing that, I shared the screen. Hmm. In my previous videos, I have applied the Euler method, forward Euler method, and also I have applied the Matlab solver OD45. So in the previous video, I have done those kind of things. Today, I will try to apply the second order Runge-Kutta method. So yeah, if you write second order Runge-Kutta method in Google, so it will give some pictures, and so one of the pictures is this one. I have to actually pick a formula or pick a method. Then I will discretize the SIR model using this. So you can say method. This method is used for any journal scalar differential equation. So the SIR model is not a scalar; it's a system of equations. So I have to use this method for system of equations. So this is the second order Runge-Kutta method. I put the picture on the board, and now I will put the SIR model on the. Even the SIR model can be taken any SIR model or SCIR model or this kind of models you can pick from any research paper. So just using the standard, the basic one. So you can use similarly on the similarly you can apply the method on some other epidemic model. So on any differential equation. So I just picked this model. So you can pick any other model as well. So for SIR, okay, the main advantage of second order Runge-Kutta method is actually it is consistent on two time level. So or two grid points. It finds the solution at n plus one or I plus one grid point, uh, and also but it finds the solution at I plus one using the solution at I minus one at I minus one grid. So that's the main advantage of that method. And also it provides second order records. The fourth order indicator method I will try to apply in my next video, maybe. Yeah, next video. For this video, I will second order. So this is an epidemic model using. So, so first component, look at that. Here in the register, it says V1. It can be any V1, U1, any P1. So if I use V1 for the first equation in Runge-Kutta and for first equation in SIR model, H is the step length. It can be delta T or it can be H. Then it says that F of, what is F of XY? This thing is F of XY, the right hand side of each equation. The right hand side of each equation is F of XY. If the equation is not written into this form, then you will first convert the equation into particular form. So this is the particular form in which the derivative on one side and the remaining thing on the other side. So I will use this thing, the remaining thing on the from the right hand side. So I will write first that it says it is evaluated at nth grid point or ith grid point. So I write minus beta in. It can be I at I. Okay, I write I at I. And then SI. And then V2. V2 it is H. And then whole function, because there is this function, these equation does not contain any independent variable. Only the derivative of dependent variable is equal to independent variable, but the independent variable is not multiplying or adding with some other. So therefore, this thing xn will not appear in this formula. Xn will not appear here. Xn is the independent variable. Yn is the dependent variable, and here Yn there are three Yn. One is S, other is I, and third one is R. Three dependent variables. So here, what I will write for V2 is H, then this at the right hand side of second equation, which is evaluated at ith grid point. So it's beta I at I, and S at I minus gamma I. So that you should say this thing I use this kind of, you can say understand in this way. No, sorry. This thing I use first this thing for the first equation, for the second equation. Now apply this thing for the third equation. For the third equation, suppose that I use V3 H into gamma I. Gamma. So I use I and instead of I. So this thing here it will be I. It is I here. So it is gamma II. So this is the first equation. So first equation of second order Runge-Kutta method. This is the first thing. Suppose that there are three kind of equation. The one is this, second one is this, and the third one is this. So I applied the first equation of Runge-Kutta onto that particular first equation of the model. Now I'll apply the second method of the Runge-Kutta method. Second formula for the Runge-Kutta method. For second formula, I give the name as V. Remember that this V2 is not same as this V. So this V2 is different. It actually corresponds to second equation. And that V2 is the second formula in Runge-Kutta. So now I have V12. V12 is the second formula for the Runge-Kutta method corresponding to first equation of SIR model. For the first equation will be discretized as H into minus beta, then I at I plus 1 by 2, 1 by 2 previous component of I. Previous component of I is the V2. So it will be V2 multiplied by SI plus of. Now I will use what I will use. I will use the component for SI. This is the first component. So V1. Previous component for susceptible, which is V1. So I'm using V1 here. V1 here. And then what about V22? No, this is the second order of Runge-Kutta method corresponding to second equation. So that's H, and then beta I at I plus of V2. So this thing. So instead of I wrote I at I plus half V2. This thing. Similarly, that component will be S at I plus half previous component of the susceptible, which is V1. I raise this thing, and then next minus gamma I. So it is I at I plus 1 by 2. The previous component for I is V2. So I add half V2 here. And the third one is that V32. V32 is corresponding to this one. So that would be H into gamma into I at I plus half V. Previous component of I is V2. So I use V2. And now I will use the last stage of the method. So last stage of the method is Si again. Si plus 1 is Si. Suppose that this would be a first stage, and then second stage. Oh, sorry, not first stage. These all are first stage, you can say, and these all are second stage, you can say. And now I will write the final thing. And this is the third stage. So it's a Si plus, it says a V2, the previous component. So Si plus, here I will write V12 instead of V2. For susceptible, this is the first equation. So that's the first equation, and then I at I plus 1 is equal to I at I plus, instead of I, you can write N here. So I, for previous component of V is V22. So I write V22. And now for third one, I would have Ri plus 1. Ri plus 1 is equal to Ri plus previous component of recovered, which is V32. So V32. Now I will construct the code for this. In my previous video, I constructed the code for Euler method, but now I will construct the code for this Runge-Kutta, second order Runge-Kutta method. So these are the basic things: T naught, T1, N, and then T variable was supposed, and then dt, the step size, beta and gamma are the parameter appear in SIR model. S, I suppose the dependent variable with n rows and one column. I also suppose I as n rows and one column and R say. And these are the initial condition S1, I1, and R3. Sorry, S1, I1, and R1. So now I will commit this. So if I commit this, so the Matlab will not read these lines. So now, first, what the thing there? First, it is V1. So I write V1 here. V1 is equal to H. Instead of H, I use DT because I have used the DT. DT into minus beta multiplied by I at I multiplied by S at I. That's a V1. And then V2. V2 is dt multiplied by beta I at I, and then S at I minus gamma into I at I. Now V3 is equal to dt gamma multiplied by I at I. So that was the first stage. Now I move to the second stage of the Runge-Kutta. Second stage is this one. So second stage will be V12. V12 is equal to dt multiply by minus beta minus beta I at I plus 0.5 B2 multiply S at I plus 0.5. So V22 is equal to dt multiplied by beta at I plus 0.5 V2 S at I plus 0.5 V1 minus gamma I at I plus 0.5 V2. And then V32 is equal to dt multiplied by gamma I at I plus 0.5 V2. So Si plus 1, third stage would be that is Si plus V1. So I plus I is equal to II plus V2. Then I plus I plus 1 Ri plus V3. So this is the method. I can compare the result with the OT45 MATLAB solver. If I do that, what I will get? I run the code. So here is the problem. Instead of multiplication, I equal sign. Again, and, oh, beta here. Beta is equal to 0.1 and gamma is equal to 0.1. No, that's a difference of the absolute error for the so that absolute error is obtained by subtracting the OD45 solution from this one, or you can say difference of two solutions, absolute value of difference of two solutions. So that's the error. You can say the error. And so this was the Runge-Kutta method which was applied to the SIR. So now I end this video. So in the next video, I will try to apply the fourth order Runge-Kutta method to the SIR model. Okay, bye.